Okay, so our second portion here on gases, we're going to look at two laws. We're going to look at Avogadro's law first here, and then we're going to look at the ideal gas law. So with Avogadro, he stated that equal volumes of gases at the same temperature and the same pressure contain equal numbers of molecules. So if they contain equal numbers of molecules, they also contain equal numbers of moles. So this is a relationship between the number of moles and the volume. And so what he said is that as the amount of the gas increases, so as we add more molecules, we're adding more moles, the volume will increase. So this is a direct relationship. So if you look down here, we have the mathematical statement of the law. So V1 over N1 equals V2 over N2. So as we increase the number of moles, we're going to increase the volume. The other way to look at it, because sometimes it's not super useful, is basically that the ratio of the volume to the number of moles is a constant. And it doesn't matter what gas we're talking about, that ratio is always going to be the same. Okay, so what we can do is we can actually apply this to some problems. So which of the following samples of gases occupies the largest volume, assuming each sample is at the same temperature and pressure? So we have, in this case, we have the same amount in terms of mass of each. So what we have to do is we have to actually figure out the number of moles, because remember, mass doesn't tell the whole story. So in this case, what we're going to do, first of all, we'll start with neon. So we figure out the number of moles of neon. So we take 50 grams of neon, and then we use the molar mass of neon from the periodic table to determine that we have 2.48 moles of neon. Then we do the same thing for argon, and we have 1.25 moles of argon. And lastly, we do xenon, and we end up with 0.381 moles of xenon. Now, what that does is it allows us to compare basically apples to apples. So what I can do is I can say, okay, we know that as the number of moles increases, the volume increases. So the one that has the largest volume is going to be also the one with the largest number of moles. So in this case, since neon has the highest number of moles, it's going to have the largest volume. And it really is just that simple. We just have to get everything into moles, though, so that we are comparing, like I said, apples to apples. All right, so part B here. Given that 1 liter of nitrogen reacts with 3 liters of hydrogen to produce 2 liters of ammonia. Okay, so this would be our equation. That's essentially what that is saying, and that is balanced. So how many molecules of hydrogen react with 1 molecule of nitrogen? Okay, we have 3 molecules, okay? And how many molecules of ammonia are produced for every molecule of nitrogen consumed? So for every one of these, we get 2 of those. How many molecules of hydrogen are consumed for every 6 molecules of ammonia? So I have to multiply that by 3, okay? And that would give me 9, because I have to multiply both of them by 3, okay? Now, letter C, don't worry about this problem because we're going to get to this shortly, okay? Because we're comparing different gases. So we're going to get to that here in a little bit. We're going to get to that in stoich. So the second law we want to look at today is the ideal gas law. And basically the ideal gas law pulls in this concept of moles, finally, with pressure and temperature. Okay, so any gas, it says, can be described in terms of its pressure, its temperature, and the amount present. So the pressure has to be given in atmospheres or kilopascals. So if you're given the pressure in something else, you're going to have to convert, like we talked about last time. Okay, temperature, again, this has to be in Kelvin. It cannot be in Celsius. Volume needs to be in liters, not milliliters. And the amount needs to be in moles. Okay, so the individual gas laws that we talked about before describe these relationships between these variables. And basically what the ideal gas law does, it takes all 4 variables that describe a single gas in one given set of conditions. So this is the equation that we use. PV equals nRT, and we know what everything is in there except for R. R is what we call the universal gas constant, and there are 2 options for it. R can be 0.08206 atmospheres times liters over moles degrees Kelvin, or it can be 8.314 kilopascals times liters over moles degrees Kelvin. These are both listed in the reference folder, but you are going to need to choose the appropriate R for the problem you are solving. So you need to see, basically the only difference here, besides the number, is which pressure you are using. Okay, don't forget that the N is the number of moles, so we take the mass divided by the molar mass, okay, and that density is mass over volume. Okay, so what we're going to do is we're going to walk through 3 different problems here. And so the first one, calculate the volume of a gas balloon filled with 1 mole of helium with the pressure when the pressure is 760 torr and the temperature is 0 degrees Celsius. Now, before I can even start anything, I have to do a couple of conversions. Okay, but don't forget, we're going to be using the equation PV equals nRT. How I know this is because I've got one gas under one set of conditions. Okay, but like I said, I need to change a couple of things. First of all, my pressure, it's in torr. That's not going to work with R, so I have to change it. 760 torr is 1 atmosphere. The second thing I need to change is my temperature. My temperature is in degrees Celsius, and that won't work either. So 0 degrees Celsius is 273 K. Once I have that, I can plug things in. So I have 1 atmosphere. V is what I'm solving for because that's what it says calculate the volume. I have 1 mole, that's from the problem. I choose this R because it's in atmospheres, which is what I changed my pressure to. Now, if I changed it to kilopascals, 101.3, I could use that R instead, and that's fine. I'll still end up at the same place. And then my temperature, 273 K. Once I do this, I come up with 22.4 liters. And if you notice, that's the molar volume that we are used to seeing. And if you look, this is standard temperature and standard pressure. So this is actually how we experimentally determined what the volume of any gas would be. 1 mole of any gas is 22.4 liters. It doesn't matter if I'm talking about helium. It doesn't matter if I am talking about xenon. Okay, they're different masses, but as long as I have 1 mole, both of them are going to occupy 22.4 liters. Okay, problem 2. Calculate the pressure, and we want to go in atmosphere, so that actually helps us pick our R, exerted by 54 grams of xenon in a 1 liter flask at 20 degrees Celsius. Now, we have a couple of conversions we have to do here. First of all, grams. I can't work with grams. I need moles, so we can do that conversion. 54 grams of xenon, okay, converting that with the molar mass gives me 0.411 moles of xenon. The second one, I have degrees Celsius here. Can't use that either. Need to be in Kelvin. Okay, so 20 degrees Celsius is 293 K. Now I can use my PV equals nRT and plug in. All right, so my P is what I'm solving for. I'm at 1 liter flask. I've got my number of moles that I just calculated. Since I want my pressure in atmosphere, this is the R that I choose, and I have 293 K. When I rearrange and solve, I get 9.88 atmospheres. Okay. And the last problem under the ideal gas law, and the last one we're going to do in this video, is to calculate the density of nitrogen dioxide in grams per liter at 124 atmospheres and 50 degrees Celsius. So I need to, first of all, make sure that I have my temperature in Kelvin still. And the other thing, because I've got grams here, I know I'm going to have to take moles into grams, so I'm going to need the molar mass. So the molar mass of nitrogen dioxide is 46 grams per mole. And if you need review on how to do that, just come see me. All right, and my 50 degrees Celsius is 323 K. Now, when I plug this in, what you will notice is into my PV equals nRT, I actually have 2 variables here that I don't know. Okay, I have my number of moles and I have my volume. Now, and I plug in, I've got my atmosphere, so I choose this R and I have my temperature. When I rearrange this, if you look, density is mass over volume. So I'm going to solve this and put my number of moles over my volume. So when I rearrange this, I get moles over volume is 0.046782, and I know I'm going to need 3 sig figs. Okay, so then I reduce that down to 0.0468 moles per liter. Okay, but the challenge is moles per liter is not what I want, but I can change my moles into grams. So all I need to do then is use the molar mass. So I take my moles per liter, multiply by my molar mass, and I get my final answer, which is the density at 2.15 grams per liter. Now, having gone through these two gas laws, you should be able to do the problems on the gas laws side B, or gas problems B, which are the ideal gas law.